Dear students, hope all you are doing very fine. Today in this lecture, I will explain very important topic of particle in one dimensional box, especially focusing on the wave functions. I am Dr. Pushpal Ghosh, an assistant professor in the Department of Chemistry at Dr. Hari Singh Gour Central University, Sagar, Madhya Pradesh. Today explain the topic in front of you, and the writer of this content is Dr. Moutusi Manna, who is a senior scientist at Central Salt Marine and Research Institute, CSMCRI, Bhavnagar, Gujarat. In this module, you will learn normalization of wave function and complete solution, characteristics of wave functions. I will explain orthogonality property of wave functions. Then I will explain how wave associated with the particle, and these are stationary waves. Then I will explain some applications, for example, average position and momentum of the particle. Also, I will explain uncertainty in position and momentum of the particle, as well as spectroscopy of the particle in a box, and very importantly the selection rule for electronic dipole transition. Then I will summarize my lecture. In the previous class, we have considered a hypothetical situation in which a particle of mass m is confined to move freely in a finite region of space along one dimension between x greater than 0 less than L. The problem is called the particle in a one dimensional box. The quantum mechanical treatment of the particle gives rise to a large number of allowed energy levels. For example, E n is equal to n square h square by 8 ml square, where the quantum number n is equal to 1 to 3. We found that the particle can have only discrete energy values depending on the quantum number n, which you can see in the screen as figure 2. Moreover, the particle is never at rest. The lowest kinetic energy of the particle in a box is called the 0 point energy, which I have explained in last class. Those properties of the particle are in striking contrast to the classical results. The quantization of energy is a consequence of the boundary condition that the wave function psi n x of the particle have to satisfy in order to be acceptable. Now, we will study the solutions of psi n x, its characteristics and some applications. The wave functions of various state of the particle in a box are given by this equation psi n x is equal to b sin n pi x by L, where n is equal to 1 to 3, which is designated as equation number 1. According to Born interpretation, the probability that the particle is located between x and x plus dx is psi n star x psi n x dx is equal to b star b sin square n pi x by L mod b square sin square n pi x by L. Therefore, the probability of finding the particle over all space is integration minus infinity to plus infinity mod psi n x square dx is equal to 1, which is designated as equation 2. Now, the value of arbitrary constant b will be determined using the normalization requirement, which is shown in equation 2, and according to figure 1 displayed in the screen, we can rewrite equation 2 as minus infinity to 0 mod psi n x square dx plus 0 to L mod psi n x square dx plus L to infinity psi n x square dx is equal to 1. The potential energy V x of the particle outside the box is infinity, which you can see from the figure 1. Therefore, the particle is at all times somewhere in the box. The probability that the particle lies between x is equal to 0 and x is equal to L is thus unity. Outside the box, that is in region 1 and 3, the probability of finding the particle is 0. Therefore, we must have this equation 0 plus 0 to L mod b square sin square n pi x by L dx plus 0 is equal to 1. So, we can write this mod b square 0 to L sin square n pi x by L dx is equal to 1, which can be known as equation 3. We know that a function sin square theta is equal to half into 1 minus cos 2 theta, and from equation 3 we then have mod b square 0 to L half 1 minus cos 2 pi n x by L into dx is equal to 1. So, we can write this by rearranging mod b square third bracket start half 0 to infinity 0 to L dx minus half 0 to L cos 2 pi n x by L dx is equal to mod b square L by 2 minus 0 is equal to 1, or we can get the mod b is equal to root over 2 L. This is the absolute value of b, thus b can be root over 2 L or minus root over 2 by L. Moreover, b need not be a real number and can be a complex number with absolute value of root over 2 by L. Thus, we can say that b is equal to root over 2 by L e to the power I alpha, where alpha is the phase of b and can be any value in the range of 0 to 2 pi. Choosing the phase to be 0, the stationary state wave functions for the particle in a box are psi n x is equal to root over 2 by L sin n pi x by L, where x greater than 0 and less than L and n is equal to 1 to 3. This can be designated as equation 4. Also, psi n x is equal to 0 in the other place we can say or elsewhere. So, therefore, the complete solution to the problem which we discussed since the last class, that energies is equal to E n is equal to n square h square by 8 ml square, and wave function psi n x is equal to 2 by L sin n pi x by L, where n is equal to 1, 2 and 3. The wave function and probability densities of some quantized states are shown graphically in figure 3, which you can see from the screen. In the first quantum state, that means n is equal to 1, there is a fair probability of finding the particle anywhere in the range x greater than 0 less than L, although the most probable position is at L by 2, that is at the center of the box. Whereas, in the second quantum state, that is n is equal to 2, the probability of finding the particle at L by 2 position is 0 and is maximum at the midpoints of hubs, that is L by 4 or and 3 L by 4. The point where the wave function is 0 is called node. For each increase in the value of n, there is one more node in psi n and mod psi n square. For nth state, there are n minus 1 nodes. According to classical physics, a macroscopic particle is equally likely to be found at any point of the box, as it bounces back and forth elastically between the two walls at a constant speed. But the behavior of microscopic particles cannot be fully and correctly described in terms of the concept of classical physics. The existence of nodes in psi and psi square thus may appear surprising. Quantum mechanically, we find that the probability of finding particle at various points are quite different than the classical results. For the lowest energy level, the most probable position is at the center of the box, which is seen in figure 3 in the screen. For n is equal to 2, the particle is equally probable to be found on the both sides of the box without at any time being found in the center. But at higher energy level with more nodes, the maxima and minima of probability come closer. Figure 4 in the screen, you can see that the probability density for n is equal to 20 is mod psi 20 square is fairly uniformly distributed between the range x greater than is equal to greater than g and x less than L. Thus, as we go to very high energy levels, the variation in probability along the length of the box become undetectable. We approach the classical result of uniform probability density for high quantum numbers. These results illustrate the Bohr correspondence principle which we have discussed earlier, and according to which in the limit of the large quantum numbers, quantum mechanical results tend to agree the classical mechanical results. The large quantum number limit is often called the classical limit. Now, let us imagine a one-dimensional mirror placed at the center and parallel to the walls of the box, which you can see in the dotted line in the figure 3. This reveals another interesting feature of the wave functions, that they are alternatively symmetric and antisymmetric with respect to the reflection from the mirror. For example, for n odd, psi n is symmetric, show that psi n minus x is equal to psi n x. For n even, psi n is antisymmetric, show that psi n minus x is equal to minus psi n x. Let us consider that psi n and psi m are wave functions corresponding to different energy levels E n and E m characterized by quantum numbers n and m respectively, where n not equal to m. Then we can write minus infinity to plus infinity psi n x psi m x dx is equal to 0 to L psi n x psi m x dx is equal to 2 by L 0 integration 0 to L sin n pi x by L sin m pi x by L dx. Now, the above integral will be evaluated with identity, that we can take a formula like if sin n theta and sin m theta, then we can write it as half into cos n minus m theta minus cos n plus m theta. Hence, we can write 2 by L 0 to L sin n pi x by L sin m pi x by L dx is equal to 1 by L integration 0 to L cos n minus m pi x by L minus cos n plus m pi x by L dx is equal to 1 by L pi into L by n minus m sin n minus m pi x by L minus L by n plus m sin n plus m pi x by L in the range of 0 to L, and after putting the value of 0 L, you can find the value of it is 0. Thus, we can write minus infinity to plus infinity psi n x psi m x dx is equal to 0 when n not equal to m. Therefore, the wave functions for different states of the system are orthogonal to each other. This ensures that the various states are independent of one another. Thus, the wave function of the particle in a box form a complete orthonormal solution or complete orthonormal set if this satisfy the following condition, that is minus infinity to plus infinity integration psi n x psi m x dx is equal to 1 where n is equal to m, and minus infinity to plus infinity psi n x psi m x dx is equal to 0 where n not equal to m. The wave functions associated with each quantized states, that means n is equal to m, are normalized. The wave functions corresponding to different energy levels are orthogonal. The wave functions of the particle in a box are sine waves, and we can write psi n x is equal to root over 2 by L sin n pi x by L, where n is equal to 1, 2, 3, etc. We know the equation of a sine wave is psi is equal to a sin 2 pi nu t, which can be written as a sin 2 pi c by lambda into t or a sin 2 pi x by lambda, where a is the amplitude, psi is the frequency and lambda is the wavelength, c is the speed and t is the time. Comparing the above two equations, which I have just stated earlier, we find that the length of the box L is integral multiply of lambda by 2, which can be seen in figure 3, where lambda is the wavelength of the wave function psi n x associated with the quantized n state of the particle in a box. So, we can write L is equal to n by t lambda. This is an essential condition for a standing wave, which is a very important formula of the classical physics. The wave function of the particle in a box are therefore standing or stationary waves. Now, from de Broglie's equation, the momentum associated with the particle is p is equal to h by lambda, where n h by 2 L, where h is the Planck's constant. Thus, the kinetic energy of the particle, we can write that E is equal to p square by 2 m, which is equal to n square h square by 8 ml square, which I have discussed or which we have derived in the last class. Now, I will discuss some problems, though I will not discuss all, but I will just give the hint how to solve it. For example, let us take a problem that calculate the probability of finding the particle between 0 and L by 2 in a one dimensional box of length L. Its answer will be half, and I can give you just a clue to solve it. That means write psi n star x psi n x dx is the probability of finding the particle between x and x plus tx. So, probability of finding the particle within an interval x greater than is equal to x1 and less than is equal to x2 is x1 to x2 integration psi n star x psi n x dx. So, we know that the wave function for the particle in a one dimensional box of length L is psi n x is equal to root over 2 by L sin n pi x by L. So, this is enough clue which I have given. Now, you can solve it. Now, another problem you can solve it, that find the position of nodes and antinodal points of psi 5 and you can plot psi 5 for the equation that sin is equal to root over 2 by L sin n pi x by L and x between 0 to L. So, the clue is here that at nodes you know the value of psi n is equal to 0 and the antinodal point, that is the maxima and minima, is equal to d psi by dx, and if you solve it you can find that nodes at x is equal to L by 5, 2 L by 5, 3 L by 5 etc. and antinodes occurs at L by 10, 3 L by 10, 5 L by 10 and 7 L by 10 etc. Now, another important point you can solve it. For example, let us say we know for a particle in a one dimensional box of length L is sin is equal to root over 2 by L sin n pi x by L when x varies from 0 to L. Now, consider a new coordinate system x greater than is equal to minus L by 2 less than is equal to L by 2 and you can calculate the energy and the wave functions. So, I am not going to discuss these things, you can solve it. Similarly, another problem also I have given which you can try at your home. And the average value of x or the mean position of the particle is given by that x average is equal to 0 to L integration psi n star x psi n x dx is equal to, we can write 2 by L 0 to L integration again x sin square n pi x by L dx, which you can write in equation 5. The value of the integral in equation 5 is L square by 4. Now, students, you can try to evaluate the integral by yourselves. The integration can be evaluated using again one formula, that sin square theta is equal to half into 1 minus cos 2 theta. Thus, average x you can write 2 by L into L square by 4 is equal to L by 2. So, this is a physically expected result as the particle is trapped between the two walls at x is equal to 0 and x is equal to L, and so by symmetry average x must be L by 2. Now, I can discuss how you can calculate the average momentum. Now, the average momentum of the particle in a box is given as that p x average is equal to 0 to L integration psi n star x p x operator psi n x dx. We know the linear momentum operator p x cap is equal to minus I h cross d by dx. Thus, we have the average p x is equal to 0 to L integration 2 by L to the power half sin n pi x by L into minus I h cross del by dx again into 2 by L to the half sin n pi x by L dx. Now, if you solve it, you can find it will comes to minus I h cross 2 n pi by L square 0 to L sin n pi x by L cos n pi x by L dx is equal to 0, and after integrating you can find the value of average momentum is p x average is equal to 0. So, the average linear momentum of the particle is 0 as the particle in a box is equally likely to move in either direction. Now, I will explain another very important topic because you know that I have explained earlier uncertainty principles. Now, I will discuss how you can calculate the uncertainty in the position and uncertainty in the linear momentum. Now, the root mean square deviation of any parameter is known as the uncertainty in the parameter. So, the uncertainty in the position of the particle in a box is delta x is equal to root over x square average minus x average square. We have just calculated the average value of x, and you already learned that average value of x is equal to L by 2. Similarly, x square average is 0 to L psi n star x square psi n x dx, which can be equal to L square by 3 minus L square by 2 n square pi square. Again, the students can try to solve this issue to solve this integral. Thus, we can write delta x is equal to root over x square average minus x average square, which can be simplified as root over L square by 3 minus L square by 2 n square pi square minus L square by 4. So, you can write root over L square by 12 minus L square by 2 n square pi square. So, again by simplifying you will find it, the delta x is equal to L by 2 n pi root over n square pi square by 3 minus 2, which can be designated as the equation 6. Now, you can calculate the uncertainty of the momentum. The uncertainty in the linear momentum is delta px is equal to root over px square average minus px average square. We have calculated above the energy value of linear momentum, that is px average is equal to 0. Similarly, px square average is equal to 0 to L psi n star x px cap square psi n x dx. Again, if we can put the value of psi n and psi n star and psi n, we can found that 0 to L 2 by L to the power half sin n pi x by L into minus I h cross d by dx square into 2 by L to the power half sin n pi x by L dx. So, average px square is equal to n square pi square h square by L square. Thus, px is equal to root over n square pi square h square by L square, which is equal to n pi h by L, and you can put this equation as equation 7. So, the equation 6 and 7 show that the more one tries to locate the particle by reducing L, the greater will be the uncertainty in the linear momentum and vice versa. So, the product of two uncertainties is, we can write delta x and delta px is equal to L by 2 n pi into root over n square pi square by 3 minus 2 n pi square h by L is equal to h cross by 2 root over n square pi square by 3 minus 2, and you know that the value of root over n square pi square by 3 minus 2 is never less than unity. So, we can write delta x into delta px greater than or equal to h cross by t, which is very well known as the Heisenberg uncertainty principle for when the position and momenta as a conjugate coordinate. Now, an electron in a box has a large number of discrete energy levels. On suitable excitation, the electron may undergo transition from one to another energy level. The energy associated with an electronic transition between nth and n prime level is given by delta is equal to n prime square minus n square into h square divided by 8 ml square. Now, from Bohr's theory, the frequency nu of transition is nu is equal to delta E by h is equal to n prime square minus n square by 8 ml square into h. So, the wavelength lambda of the transition is lambda is equal to c by nu is equal to 8 m c L square by n prime square minus n square into h. The longer is the length of the box, the longer is the wavelength of the electronic transitions. Therefore, by adjusting the length of the box, the wavelength of an electronic transition can be made to appear in the visible range of the spectrum. This is very important, you have to remember. The system then appeared colored. So, now you understand how different color origin is coming. However, the transition between any two levels is not allowed. A transition occurs when the oscillating electrodipole undergoes resonance coupling with electromagnetic radiation of comparable frequency. The transition probability of an electronic dipole transition depends on the magnitude of the transition dipole moment integral, which is designated as mu n prime n, which must be non-zero for transition to happen, and we can write the mathematical equation that mu n prime n is equal to E integration 0 to L sin prime x cap sin dx is equal to 2 E by L 0 to L sin n prime pi x by L x sin n pi x by L dx. Let pi x by L is equal to theta. Thus, x is equal to L theta by pi and dx is equal to L by pi d theta. Now, putting these values in above equation, we have mu n prime n is equal to 2 L e by pi square integration 0 to pi sin n prime theta sin n theta theta d theta. Now, after solving this integration, we will find the 2 L e by pi square third bracket half 0 to pi integration cos n minus n prime minus n theta theta d theta minus half 0 to pi integration cos n prime plus n theta theta d theta is equal to, you will get L e by pi square into L1 minus L2, which can be designated as equation 8. Now, you can solve that, or you can say that where L1 is equal to 0 to pi cos n prime minus n theta theta d theta. After solving again, you will find 1 by n prime minus n second bracket theta sin n prime minus n theta in the range of 0 to pi, and again integration 0 to pi sin n prime minus n theta d theta. After solving this, you can get again 0 plus 1 by n prime minus n square cos n prime minus n theta in the range of 0 to pi, and you can find after solving this 0 plus 1 by n prime minus n square minus 2 if n prime minus n is an odd number, or it will be 0 if n prime minus n is an even number. So, this is very important, because again I am repeating here that the value of L1 which you found that its value will be 0 plus 1 by n prime minus n square minus 2 when n prime minus n is an odd number, and when it will be 0 when n prime minus n value is an even number. So, you have to remember these things very importantly. And similarly, you can calculate the L2 also, and L2 you can found that 0 to L integration cos n prime plus n theta theta d theta. After solving, you will again find 1 by n prime plus n second bracket start theta sin n prime plus n theta in the range of 0 to pi minus integration 0 to pi sin n prime plus n theta d theta, and again you can get 0 plus 1 by n prime plus n square cos n prime plus n theta 0 to pi, again 0 to 0 plus 1 by n prime plus n square minus 2. So, if n prime plus n is an odd number, again 0 if n prime plus n is an even number. So, in last when we solved L1, and there we have told that when n prime minus n is an odd number, we get the value, but when n prime minus n is an even number, we got the value of 0. But here you can see that in case of L2, when n prime plus n is an odd number, we are getting some value, but when n prime plus n is an even number, we are getting the value of 0. So, thus we find that mu n prime n does not vanish if n prime plus minus n is an odd number. That is I am mentioning two times, because if it is odd number, it does not vanish. Thus, the selection rule for electronic dipole transition is stated as a transition between a pair of states is possible if the sum of or the difference in quantum numbers is an odd number. If both are even numbers, the transition is said to be strictly forbidden. So, you can get that in case of even number it is forbidden, but in case of odd number it is allowed. So, according to the selection rule, a transition is possible from n is equal to 1 to n is equal to 2, n is equal to 4 state, or but not possible from n is equal to 1 to n is equal to 3, n is equal to 5 state. Okay. So, again I am repeating the selection rule that a transition between a pair of state is possible if the sum of or the difference in quantum numbers is an odd number. If both are even numbers, the transition is said to be strictly forbidden. So, the knowledge of the selection rule is of great importance in spectroscopy, as it predicts whether a theoretical transition is allowed or not. The above selection rule may be varied by using symmetry argument. As we discussed above, the wave functions psi nx are alternatively symmetric, that is n is equal to 1, 3, 5 etc., and antisymmetric n is equal to 0, 2, 4 etc. with respect to reflection through the center, which you can see in the figure 3. If under symmetry operation an integral changes sign, it will have a particular value in one part of the space which is equal and opposite of the value over another part of the space. The integral over all space thus will become 0, but if the integral does not change sign, we will get non-zero value on integration over all space. So, now from this you understand that how the spectroscopy can be a great application of the quantum mechanics, and your syllabus is very much interlinked with the spectroscopy and quantum mechanics. For example, first you have learned some basic principles of spectroscopy, then we taught you some basic of the quantum mechanics, and using particle in one dimensional box you try to understand, or you have understood already, that how energy can be calculated, how wave functions can be generated, and what are their properties. Okay, that is very important. For example, I explained to you earlier that how using operator you can calculate the eigenvalues, like eigenvalues. For example, you are able to calculate energy using the Hamiltonian operator H. Now you understand from this today's lecture that how spectroscopic selection rules can be generated or can be useful to understand the electronic transitions. In the following course, in the next lectures, maybe you will listen some or lectures related to the rotational spectroscopy, vibrational spectroscopy, Raman spectroscopy, and then again there you will find that selection rules are playing important role there. Now I can summarize my lecture today. That summarizing, we can find that we have derived the complete solution of the translational motion of a free particle in a one dimensional box. We have learned that only certain wave functions are acceptable, which I also explained last class too. The permitted energies and wave functions of the particle are energies is equal to E n is equal to n square h square by 8 ml square, where the quantum number n is equal to 1, 2, 3, and wave functions is equal to sin x is equal to root over 2 by L sin n pi x by L. So, using the wave function we can evaluate many observable properties of the particle in the box, like its position, linear momentum, and associated uncertainties. Using the solution of this simple problem, we determined the selection rule for electronic dipole transition, having great importance in spectroscopy. And I must mention here that I am Dr. Pushpal Ghosh, Assistant Professor in the Department of Chemistry, Dr. Hari Singh Gaur Central University, today presented this lecture in front of you. And the content of this material is written by Dr. Moutusi Manna, who is a senior scientist in Central Salt and Marine Research Institute, CSMCRI, Bhavnagar, Gujarat. Thank you very much for your kind attention.